All right, welcome to day 17 of Advent of Code. I'm going to go straight into today's question. Yesterday's one was super fun, but it took ages, hoping that today's one will be a little bit shorter. So here we go. Day 17 trick shot. You finally decode the elves message. Hi, the message says. You continue searching for the sleigh keys. Ahead of you is what appears to be a large ocean trench. Could the keys have fallen into it? You'd better send a probe to investigate. The probe launcher on your submarine can fire the probe with any integer velocity in the x, forward, and y upward or downward or negative directions. For example, an initial velocity of xy like 0, 10 would fire the probe straight up, while an initial velocity like 10 minus 1 would fire the probe forward at a slight downward angle. 10 minus 1. Okay, so minus 1 points down. Yep, that makes sense. The probe's xy position starts at 0, 0. Then it will follow some trajectory by moving in steps. On each step, these changes occur in the following order. The probe's x position increases by its x velocity. The probe's y position increases by its y velocity. Due to drag, the probe's x velocity changes by 1 towards the value of 0. Okay, that is decreases by 1 if it's greater than 0, increases by 1 if it's less than 0. It does not change if it's already 0. Okay, so moving towards 0. Due to gravity, the probe's y velocity decreases by 1, right? So it always decreases. It's quite straightforward. For the probe to successfully make it into the trench, the probe must be on some trajectory that causes it to be within the target area after any step. The submarine computer has already calculated this target area for you, your puzzle input. Okay. Right. Okay. For example, this one. This target area means that you need to find an initial xy velocity values such that after any step, the probe's x position is at least 20 at most 30, and the probe's y position is at least minus 10 at most minus 5. Given this target area, one initial velocity that causes the probe to be within the target area after any step is 7, 2. Right, so it's kind of like a parabola-ish sort of shape. In this diagram, S is the probe's initial position, 0, 0. The x coordinate increases to the right, the y coordinate increases upward. Right, yeah. In the bottom right position there, this target area, cool, I'm gonna skip that. Another initial velocity that causes the probe to be within target area is 6, 3. And this is where the drag comes in. You can see that the trajectory is, you can't see my mouse, but the trajectory has kind of just stopped at that point. Another one is 9, 0. Okay, so like a flat trajectory. But initial velocity that doesn't cause the probe to be within the target area after any step is 17 minus 4. Right, because it just skips past the area. The probe appears to pass through the target area, but it is never within it in any step. Okay, so it has to be on the step that it's in it. If you're going to fire a highly scientific probe out of a super cool probe launcher, you might as well do it with style. How high can you make the probe go while still reaching the target area? In the above example, using an initial velocity of 6, 9 is the best you can do, causing the probe to reach a maximum y position of 45. Any higher causes the probe to overshoot the target area entirely. Find the initial velocity that causes the probe to reach the highest y position and still eventually be within the target area after any step. What is the highest y position it reaches on this trajectory? Okay, let me just stare at this for a while. The first thing that comes to mind is that you can treat the x and y positions independently because they don't affect each other. The x basically slows down and stops in the target area. Right, it just slows down, which is why this 7 works, for example, because Right, because see, look here, after one more step, it's just going to stay at this position, right? Because you minus one and it never goes beyond zero. It does not change if it was already zero, which is what the 6 does. In fact, what was this area again? 20, 20, 30? Right, so isn't this just a triangle number? 6 plus 5 plus 4 plus 3 plus 2 plus 1 is, yeah, okay, which is why 6 and 7 work. 21, 8, 20, 8, 9, 10, 28. Yeah, right, because 1 plus 2 plus 3 to 6, all the way to 6 is 21, which is where this ends up. Plus 7 is 28, which is where this one ends up. So x is just the triangle numbers that, yeah, but we don't care about that because we just care about how high it goes. So we can treat this independently, right? You just shoot it up and you want it to be dropping down, shoot it as high as you can so that it drops down, and once it passes zero, it still lands within the area. And up and down should be the same, right? Yeah, look, 2, 1, 0, minus 1, minus 2, and you end up back here. So the next step is minus 3. This is 3, so 3, 3 here, and then 2, 1, 0, 1, 2, 3. So here 3, and then this is minus 4. What was the max we had? 9. Okay. Does it have a diagram of that? It doesn't. Because to 9, which means this step, it'll be 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, all the way down to this step would have been 9. So the next step here would be minus 10, which is the maximum it can be. Okay, so in fact, this is the first time I'm going to do something different. I'm just not going to use this input stuff because we don't need it for this one. This is, in fact, this is minus 10. What was that solution? 45, right? 45. So 45 is the triangle number, is a ninth triangle number. 9 times 10 divided by 2 is 45. So, okay, what's my input? Minus 126. So doesn't that mean that my initial y velocity just has to be 125? Because then this step here will be minus 126, which is the biggest it can be. In which case, is my answer just this? Oh, that is the best solution I have had yet. Just mathed it. Oh, I wish I was doing this in real time. Oh man, that is the best solution I've had yet for an Advent of Code challenge. Great. Okay, part 2. Maybe a fancy trick shot isn't the best idea. After all, you only have one probe, so you better not miss. To get the best idea of what your options are for launching the probe, you need to find every initial velocity that causes the probe to eventually be within the target area after any step. In the above example, there are 112 different initial velocity values that meet these criteria. How many distinct initial velocity values cause the probe to be within the target area after any step? Oh, that is hard. I wonder if you can, oh man, I wonder if you can systematically work this out. I'm thinking it's easy to get all the above ones, right? Like, so the way I would have thought of this was everything that is 6 or 7, then cross product that with all the y's that work, which could be probably 1, or maybe 1 won't reach far enough. But then these ones are tricky, right? Because these ones, they point down. And if they point down, like the maths is completely different again. What are the answers here? Well, okay, how about this? We know that y never gets higher than 125. Okay, right? So we know that test ranges, we know that y has to be between, it can't be higher than 125. And I guess the, like if you land in there one shot, it's like minus 126. What was my what were my values here? Let me just get these in as well. Target area. Okay, my test ranges. So we know that this is the highest you can shoot. And I guess you could just blast it straight to the target area in one shot, right? So the lowest is minus 126. And then x values can't be negative, right? There's no way they can be negative. Yeah, look, all of these x's are positive, because negative, you shoot it the other way. Doesn't make sense. So x starts from 0. Well, it can't be 0, because then it will never reach it. So in fact, this is more triangle numbers to rescue. 217, the smallest x value you could start with is the triangle number that gets closest to 217. Let's see. Gotta comment all these out. So 217 times 2, and then we kind of do a square root of it, maybe. Can I do that? Okay. 20. So 20 times 21 over 2 is 210. So 21. Right, x has to be at least 21 to reach the target area. In this example, x has to be at least 6 to reach the target area, right? At least 6. I don't think there's anything other than 6 in here. Yeah, at least 6 to reach the target area. So in my case, it has to be at least 21 to reach the target area. And I guess the maximum it can be is 240, because you blast it straight to the thing in one go. So why not just brute force it? Those ranges don't look humongous. They do not look humongous. In fact, let's just try it with this, with the test one, with the example one, I mean. So if we did the same process, we know that the target area of the example is 20 to 30, and the y is minus 10 to minus 5. So the test ranges in this case would be minus 10 to 9, going up the other way. For x, we know it's at least 6, and we know it's at most 30. So let's see, for y equals minus 10, y less than or equal to 9, y plus plus, that's my y test range. For x equals 6, x less than or equal to 30, x plus plus, that's my x test range. We fire it, right? So while what? We have max x, if tx1, tx2 is going to be 20 and 30, ty1 and ty2 is going to be minus 10 and minus 5. So for x, no, these are not y, x, and y. These are my velocities. So vx, I usually use d for these, delta x, delta y, because it's a little bit easier for me to wrap my head around. Let's see. X and y start off at 0. So while x is less than or equal to tx2 and y is greater than or equal to minus 10, which is ty1. Oh, that's confusing. We do the thing, right? We do the thing. Yeah. X plus equals dx, y plus equals dy. Due to drag, dx, if dx is greater than 0, dx minus minus. Due to gravity, dy minus minus. If x is greater than or equal to tx1 and x is less than or equal to tx2 and y is greater than or equal to ty1 and y is less than or equal to ty2, so if in target area, what do? We will successes. Just make a type for it. We'll just append it to an array like this, so we have it. Break. And then if beyond target area, if, oh, no, we already have that here. So while not beyond target area, do that. And that's it, really. We'll print this out just so we can see it. And then here we print len of successes. Oh, it's going to take a while. Okay, nope, never mind. I'm doing something wrong. Where am I going wrong with this? This is dx dy that's being printed, isn't it? How is this possible? How is y getting... What? I'm so confused. dx is 6, dx less than 30, dx plus plus, but then how is it starting off at 5? Do I have dx in here somewhere else? Oh, oh my gosh. Oh my gosh, that is so bad. initial. There we go. I'm changing the value. It's late, it's almost 11 o'clock. 112. Perfect. Okay, I'm happy with that. Let's bring in our actual data. Target area is 217 to 240. This way is minus 126 to minus 69. My test range is minus 126 to 125, and this is 21 to 240. Just to be safe, I'm going to pop in 20, although this should work anyway. Yeah, I mean that's just it, isn't it? 2, 3, 2, 1. Done. Wow. Okay. Oh, it's good. A short video. 20 minutes. We got to the answer. Yeah. Nothing much to say. I always say it. I think the first part, it was interesting in that because you realize the x and y positions are you can see that x and y are independent. You could completely ignore the x and just do the y, and there was a really simple mathematical way to do it, which was really cool. I like that bit. That's a bit different. That you can solve one of these with pure maths, no programming whatsoever. The second part I brute forced, but I feel like there probably is some way you could systematically work out which x values and which y values worked. So for example, any x in the example, right? Any x value that started with 20, 21, 22, 23, 24, 25, 26, all of those would work as long as you had a y that would put you into it as well. So basically, any of these, this was what, 11 by 6 grid, right? So that's 66 starting values that will always work no matter what straight away, because you just shoot the thing straight into it. And then you can have some x values that also work, like if you go x and x, but then because it's 2 steps of x, now you need 2 steps of y to make it work. So then that narrows it down a little bit. Starts getting a little bit tricky. And it was probably easier to just brute force it. I gave it some bounds, right? I kind of mathematically worked out the bounds of what values could work, but these numbers are so small. I guess you already worked out this bound from part 1, right? Up about the highest you could shoot it. You already worked out for part 1. So then this is really obvious. Yeah, maybe the problem really just was more like working out these bounds so that you could check all those values relatively quickly. You can see it just runs, even though I'm brute forcing it. So, yeah, really fun problem. I enjoyed it. Really nice change of pace given how hard the last couple of problems were. Yeah, so I'm going to keep these coming. Hope you enjoyed watching, and thanks for watching. I'll see you again tomorrow.